All of the atoms inside your body, from the carbon in your cells to the oxygen in your lungs, were all forged inside stars that lived and died billions of years before the sun even existed. And we even know when those atoms formed, thanks to this image from the Hubble Space Telescope of a region of space that we originally thought was empty, but instead Hubble revealed to have over 10,000 galaxies in it. Islands of hundreds of billions of stars out there in the universe, billions of light years away. That's 10,000 galaxies, all in a patch of sky smaller than the moon. But also hidden in this image is something even more extraordinary than its obvious beauty, and that is all of the astrophysics research that this image made possible, including one of the most fundamental plots in all of astrophysics, what's known as the Madau plot. It might not look as obviously beautiful at first glance, at least compared to the Hubble Deep Field, but to us astrophysicists, it is incredible because it shows us when the universe formed all of its stars and reveals that the majority formed around 10 billion years ago. Now, this plot is one of the first things that you learn about in astrophysics graduate schools because it underpins so many of our current hypotheses of how the universe has evolved from what it looked like in the early universe to what we see today, including why we're all here in the first place, because it's thanks to that big burst of star formation 10 billion years ago that enough heavy elements like carbon and oxygen and nitrogen were made in those stars and then dispersed across the universe when they died and went supernova, which then provided the ingredients to not only form planets, but for life to eventually evolve on planet Earth. So in this video, we're going to dive into all the details on this, including how you go from an image like this to a measurement of how many stars are forming at different times in the universe's history, then chat about what the Madau plot reveals and why its implications are so profound, and finally chat about how JWST, Hubble's successor, has already started to rewrite parts of this story. But before we dive into all of that, a quick word from today's sponsor, Claude. And this is one that I want to talk to you about really openly and honestly, because as a scientist, I don't take sponsorships lightly, especially when it comes to AI. In academia, I have watched the research and development of AI algorithms in the past decade and seen them go from laughable to, let's be honest, scary. Whether it's misinformation or bias baked into the models, there's huge issues with either small or large-scale use of AI and LLMs. But thankfully, Anthropic, the team behind Claude, was founded on the question of how to build AI responsibly. Their aim is to develop trustworthy AI systems while studying both the potential and the risks. They're the first to admit they've still got a long way to go, but it's their research-based approach that has really impressed me. So I gave Claude a shot, cautiously and critically, but it has now earned a spot in my workflow. Whether that's debugging code or sharpening up a draft of an abstract or even understanding niche scientific concepts. Because helping you understand complex scientific topics that you just don't have a hope in trying to Google is something that I've found Claude does really well. When I'm prepping a script for a YouTube video, I'm usually reading a paper that is outside of my research area on black holes. And occasionally in these research papers, there's the odd logical jump that just isn't documented, just because it's just ingrained in the psyche of researchers in that field. It's usually just a small thing, but getting that helps me to fully understand what my colleagues have done so that I can then translate it accurately for all of you online. And Claude's projects feature has been a real game changer for this. I can attach the papers I'm reading for each video, and Claude holds all of that context throughout, so every conversation picks up exactly where we left off. For me, Claude feels like the first AI model that actually understands the intent behind the questions that I'm asking. And I've also found it to be more honest about where our knowledge on a topic ends. So to discover for yourself why Claude feels different, thoughtful, honest, and built for real work, head to the link in the video description down below and start using Claude today. So a big thanks to the folks at Claude for sponsoring this video. And now let's get back to when the universe forms its stars and chat first about how you go from an image like the Hubble Deep Field to a graph like the Madau plot. Well, in 1996, just months after the iconic Hubble Deep Field image was released, Madau and collaborators published a paper that revealed how fast the universe was forming stars at different points in its history. So to do that, they record how much ultraviolet light each galaxy in the image is giving off. Young, hot, massive stars that have just formed give off a lot of ultraviolet light. So the more ultraviolet light you see from a galaxy, the more stars it is currently forming. And because light takes time to travel to us through the universe, because it's traveling at a set speed limit of around about 300,000 kilometers a second, we see those galaxies as they were billions of years ago. So the more distant a galaxy is, the earlier in the universe's history you're observing it. Plus, the UV light they've emitted has been stretched by the expanding universe, so much that Hubble can then detect it at the optical and infrared wavelengths of light that it's sensitive to. So with the Hubble Deep Field, we have 10,000 galaxies spanning almost the full timeline of the universe's evolution. And with it, we can work out how much star formation was happening at different points in the universe's history. So here is that data, the density of the amount of stars forming in the universe on the vertical axis, plotted against cosmic time on the horizontal axis. And this was plotted for the very first time by Madau and collaborators in 1996. And this is what became known as the Madau plot. And it's become so iconic in astrophysics because of the surprise that it gave us back in 1996. I say us, I was 6. So it wasn't me, I wasn't surprised, but my colleagues were. It revealed that star formation in the universe isn't constant. It was much higher in the past and has been declining ever since. Which brings me to part 2, what the Madau plot revealed and why it's so profound. Because at first, the results from this paper from 1996 were very tentative. There were only a handful of data points. And Madau and collaborators were really careful to refer to all of those data points as lower limits, because there was one thing they hadn't quite considered yet in all of their analysis, and that was dust. Cosmic dust, so just heavier elements that might just be single molecules all the way up to little clumps of grains. And when new stars form, they're surrounded by clouds of gas and dust, and that dust absorbs ultraviolet light before it can escape the galaxy. And so as you look at galaxies in the Hubble Deep Field, you're going to underestimate the amount of ultraviolet light they're giving off, and therefore the amount of star formation that's happening. And as more stars live and die and produce more of these heavy elements and produce more dust, it might be that instead of a drop in star formation as the universe ages, there might just be an increase in dust absorbing that ultraviolet light. So is that what Madau and collaborators had seen? Now, thankfully, infrared light, not bothered by dust. It's got a long enough wavelength that it just goes straight around all of those dust grains. So through 1998, there was then a flurry of papers that were looking at the Madau plot in infrared light, including one from Hughes and collaborators that used the James Clerk Maxwell Telescope, JCMT, on Mauna Kea in Hawaii to detect the sub-millimeter far infrared light from galaxies in the Hubble Deep Field. And they found a density of stars forming in the universe that was 5 times higher than Madau and collaborators had estimated using just the ultraviolet light. And then over the next decade, more telescopes observed more galaxies over a larger wavelength range, everything from GALEX in the UV to Spitzer in the infrared, and of course the Sloan Digital Sky Survey in visible light, all of which added more data points across more cosmic epochs to the Madau plot. So much that by 2014, Madau and Dickinson, 2 of the authors on that original 1996 paper, published a review collating data from nearly 2 decades of research on the star formation history in the universe and gave us this version of the Madau plot. This version of the plot from this 2014 review paper is the one you see all over the place. It's at the beginning of every astro graduate lecture. It's the beginning of every astro research seminar on this topic as well. I feel like I've seen it so many times now. I know it as well as I know the back of my own hand. But what we can see on this plot is that on the right-hand side, which shows what's going on in the first few billion years of the universe's life, star formation appears to be relatively modest. That makes sense if you think about it, right? Because the universe, it was still settling down. It hadn't quite built up all of the mass in galaxies yet. Gas was still too hot and turbulent to settle down and make a load of stars. But eventually, the amount of star formation rises steeply, peaking 10 billion years ago when the universe was about 3.5 billion years old. At that peak, the universe was forming stars at a rate that was anywhere from 10 to 30 times higher than it is today. This is what's known as cosmic noon. And it's also when our galaxy, the Milky Way, formed the majority of its stars. But you'll see after that peak, the amount of stars forming falls slowly but steadily as the universe gradually runs out of fuel. It means that we're sort of living right now through the long, slow sunset on the era of star formation in the universe. But what makes this so incredibly profound and what makes this, this plot so iconic is the fact that we're all here to even appreciate the Madau plot at all is intimately connected to that peak. The carbon and oxygen and nitrogen in your body was forged in stars at cosmic noon. If that peak had been smaller or happened at a different time, the chemical makeup of the universe would have been completely different at this time, and life, as we know it at least, might not have been possible. And that is what makes this one of the most iconic plots in all of astrophysics. But as we speak, this is all changing thanks to new results and data from JWST, which is now rewriting this story. Before JWST, there was only so far that we could actually see with Hubble before galaxies either became too faint or had their light shifted so much by the expansion of the universe that Hubble wasn't sensitive to it anymore. But the James Webb Space Telescope, with its much bigger mirror and sensitivity to infrared light, can detect galaxies as far back as 300 to 500 million years into the universe's lifetime. And what it's finding there is not what we expected at all. We expected to find only a few very faint galaxies, because, as I said before, the universe was still just getting started, right? Gas was still too hot, it was still too turbulent, it hadn't settled down yet, it hadn't built up the majority of mass in galaxies yet. Star formation was getting started slowly. And yet, instead, within weeks of JWST's first data being released, multiple independent research groups led by Donnan, Harry Carney, Finkelstein, and Bowens, to name a few, all showed how JWST has found lots of bright, overmassive galaxies in the very early universe that our current best models of the universe cannot explain. That means the universe at that time is forming way more stars than we expected it to, and that steep rise that we're used to seeing on the right-hand side of the Madau plot, JWST is suggesting is actually a more gradual rise to the peak, to cosmic noon. So what is going on? Well, no one really knows yet. The science is still ongoing as we speak, which means there's lots of different ideas out there to explain this. From the amount of heavy versus low mass stars that have formed being different in the early universe compared to what's formed today. I've talked about that on this channel before. Or maybe star formation is more bursty rather than constant in the early universe. Or even supernova not having as big of an effect on their surroundings, which makes star formation more efficient. And of course, it might not just be like one single explanation there. It could be a combination of a lot of those different effects. So, the next few years of JWST observations are definitely going to be focused on untangling those effects, working out which one is dominant and trying to explain this unexpected slope on the right-hand side of the Madau plot. And who knew this is where we'd be 30 years on from when that first Madau plot was published back in 1996. Starting with that single revolutionary image of the Hubble Deep Field, we've been able to build a picture of when the universe formed its stars and realize that the peak of star formation that we see at cosmic noon is why we're all even here to appreciate this in the first place. So that now we can even start asking questions using a brand new telescope, which has started to show us that that story of when the universe formed all its stars, well, that story's not quite finished. There is a plane outside. The Chinook thing that happened in last week's video, everyone was like, oh, I could hear the Chinook. I can never hear the planes that you're talking about. I don't have my engagement ring on. 1 second. Rings on past my wedding ring, so that was an error.